Hey everybody, welcome back. Good to see you again. Mr. Smith here. In the 1700s, scientists who laid down the foundations for what we know as the gas laws began to grapple with the topic in a mathematical way of thermodynamics. So as we're going to see, thermodynamics is a really broad subject, covers all aspects of how heat and matter interact with each other. We're going to begin with a couple of quick reminders. You've got an image here of a solid, a liquid, and a gas in A, B, and C. As we're going to talk about, the key feature that distinguishes solid, liquid, and gas is usually the strength of interatomic bonds. So in solids, you have strong interatomic bonds so that at room temperature, these atoms are not really free to move. In a liquid, they're more free to move, but they cling tightly. And in gases, they go pretty much wherever they want to. As you're going to see, temperature dictates how much motion they have, because temperature relates, as we'll see, to kinetic energy. And so here we've got a little animation from the American Chemical Society. They've given us a metal anvil, and if we zero in with the zoom button, they've given us a picture of atoms jostling in space. Basically accurate. The jostling is related to kinetic energy, as we're going to find out. That's related to temperature. So one of the things that we notice in solids is because kinetic energy and thermal motion are related to each other, as metals heat up, they actually change their size. So expansion grates on bridges are a common sense accommodation to the reality that bridge sections expand as they get hotter. And what we've got on this page is two formulas you want to jot down. We've got one, which is the one-dimensional expansion version. So if we think about a pencil or something like that growing lengthwise as it gets hotter, they do, that'll be your formula. If you're thinking about a volume of a liquid or a volume of a solid, there's a similar formula. And these constants right here, alpha and beta, will give you on the next slide. So the first thing you're going to notice as you look at this table, which is found in chapter 13 of our book, is that the units of these coefficients are in degrees C to the minus 1. So it's expected that the temperature changes that we feed into the formula have to be in degrees C. So that's easy enough. What we're going to do is just read this situation. They have a 100-foot long or 30-meter long section of bridge at negative 20 Fahrenheit. How much could you expect it to expand in New England? So this is a judgment call, but the hottest it might ever get in New England might be 120 degrees, let's say. So a little margin for error there. So what that does is it gives me a difference between the high temperature and the low temperature of 120 Fahrenheit minus a negative 20 Fahrenheit. So I come out with 140 degrees F. And I just plug that into that formula that you should write down, and I get the change in temperature in degrees Celsius is 60. Okay? So what we'll do is just use that in the next slide, and we're going to go ahead and go calculate that change in L. So L alpha delta T is going to look like this. We feed in the length of the bridge section as it was. We go hunt down the alpha, and so if this is a concrete section, we're going to look down here. Concrete's around 12 times 10 to the minus 6, and that's got C to the minus 1 for a label. And then we just figured out that our temperature change to be 60 or so, and when we plug this thing in, we're going to get 0.0216 meters, which doesn't sound like much. If we go and convert that in our heads to centimeters, that's 2.16 centimeters. Well, that's actually around an inch. So if you had multiple bridge sections expanding, you could get them going in both directions. So that's why expansion joints, okay? So thing one. Okay, so thing two is a little more sophisticated. If you have two materials that expand differently and they're in close proximity to each other, you can end up with issues. So this is an example of that. You have a brass bolt that's surrounded by an iron fitting, and they're going to grow it at different rates. So I have the brass that will grow with this expansion coefficient iron here. So what it looks like to me is if these two things have very, very close tolerances, the brass is going to grow, and at some temperature, it's going to start pushing against the iron fitting on the outside and maybe break it, okay? So the first question they're asking us here is what gap will exist between the materials at 200 degrees C? So the way I do this is to use a technique I wanted to show you. Sometimes the question really calls on us to figure out the new size of a thing. So the formula that I use for the new length is very simple. It's just the old length plus however much it changes by. So what you're going to see me do is, let's start with the brass because they mention it first. The new length of the brass is just going to be the original length of the brass, so 5 millimeters on the nose, plus however much it changes by. So pencil that in, and that's going to be the alpha, 19 times 10 to the negative 6, and then whatever the change in temperature is. So final temperature is 200, original temperature is 20. You should be able to get that one in your head. And that's going to be the new size of the brass. So same thing, new size of the iron, 5.008. And we'll do the same exact thing for iron and get him filled out. And same 180 degrees C. And what I do when I get this is that the new size for the iron, let's call it new size of iron, turns out to be 5.0188 millimeters, okay? So the iron has grown because it expanded. So the new size for the brass is going to be, let's check it out, 5.0171. Okay, and it looks like the difference between them is going to be smaller, and it is. The change in the gap between them, if I just subtract these two, is going to be 0.0017 millimeters. Okay, so around about 2 thousandths of a millimeter, where it started out as around 8 thousandths of a millimeter. Okay, so example number 2. Now, example number 3, it looks almost exactly the same, but I've made one important change in it. This is really a math problem that's posing as a physics problem, but it's a thing that the textbook does, and it's a good problem-solving strategy to know. So I'll show it to you. What they're asking for is at what temperature will these two things exactly fit together? And this is really why I showed you that trick a second ago. When the things fit exactly, then this should make sense that the new size of the iron is going to exactly equal the new size of the brass. Okay? And what I'm going to do is I'm going to actually lay down that formula, and then we'll talk about it. Okay, so as we've said, we have new size equals new size. Pause the deck and just write that down if you want to catch up. But what I'm going to do is just solve for delta t. So subtract 5 on both sides, do a little multiplying, and what we get is 9.5 times 10 to the negative 5 delta t is on this side equals 0.008 plus 6 and change, 0.0096 times 10 to the negative 5 delta t's over here. Swing this 6 and change delta t's over to the other side, and what I get is 3.49 times 10 to the negative 5 delta t's equals 0.008. So divide both sides, end up with delta t equals 229, and that's going to be in degrees C. Now, I just postponed, as I said, the idea of dealing with delta t until right now. This is easy. T initial was 20 degrees. It changed by 229 in the positive direction, so that tells me that T final is going to end up being 249 degrees C. Okay, so example 3. Okay, so our last example is one that's right up the alley of our future mechanical engineers. We're going to study this actual, the source of this photo in class. It was a real-life bridge collapse that happened. Never a trivial thing. It's always a big deal when a bridge collapses. But every material can expand when it gets heated, but it's sometimes possible that situations won't allow a thing to expand. So what happens is at the microscopic level, the material experiences a thing called stress, where it's trying to move and it can't move. So the formula for thermal stress looks like this one right here. Force divided by area is nothing new to you. That's actually the unit for formula for pressure. So F over A is thermal stress. Alpha, expansion coefficient, you know it now. Delta T is just change in temperature. The one thing that's new about this little formula they tuck in to this section is E is a thing called Young's modulus. Every material has one, and Young's modulus, as you can see here, is related to the stiffness or the elasticity of the material at the microscopic level. Okay, so similar to our table full of alphas, there's a table in the book in chapter 9 full of these Young's modulus numbers. So here's the example. An aluminum bar has just the right length at 15 degrees C. Someone wants to heat it up on us to a temperature of 40 degrees C, and somehow we have to keep it to the same exact size. So what stress is that going to cause inside the material? Okay, so well, we know that F over A is going to be equal to just alpha E delta T. So not a hard formula to use. Let's go get our alpha E delta T. Alpha for aluminum, we can look that up off of the other table. 25 times 10 to the negative 6. So aluminum's a little more expandy than something like steel, which has 12 times 10 to the minus 6. E, I can find it right here, is 70 times 10 to the 9. And that's newtons per meter squared. And then finally, if the material is going to go from 15 to 40, that looks like a delta T of 25. Okay, so it's really the units that I actually wanted you to pay attention to here. When I go ahead and multiply all this stuff, degrees C cancel out, and what I end up with is 4.38 times 10 to the 7 newtons per meter squared. Okay, now I said to you that this were pressure units, that F over A is the same thing as pressure. The Newton per meter squared has another name in physics. It's called 4.38 times 10 to the 7 pascals. So that is a unit you will be seeing down the road. I just wanted to point it out to you. Okay, so anyway, that's it for now. Thermal expansion. Bring some questions with you in class. We'll be working with it. Take care. Have a great day. Bye-bye.